Okay, I think it is online. Please tell someone to check.
Okay. Hello. Hello. Hello.
Yes. There might be a lag of 30 seconds on YouTube.
Yeah, that's fine.
Yes, so very good. Okay, so today we have the second speaker for this International Year of Quantum, and we have the great pleasure that we have Guru Prasad from ISI, and he did his PhD in 1997, and then he has been at ISI since 1999, and he's professor there since 2012. And I know him almost for last 30 years, and since my struggling days, trying to do something in quantum information. And that's how, so I go to library and look at the papers, and I look at his papers, and he will look at my papers. And one day we met, in PIFR conference, and he said, I have seen your paper. And I told him, yeah, I have seen your paper. That's how we got introduced. So it is very important for young generation that you should know that it's not the name is not important. You should know what should speak about yourself. Okay, so that's how we should be motivated to do research in future. And today we will talk about some historical development of quantum mechanics. So I welcome Prasad to deliver his talk.
Yeah, I'm audible. So thanks, Arun, for the introduction. Actually, there are many people whom I know, especially Professor Bhanudas. I have met him through online. And Pankaj is my friend. Ranatha was my colleague. Uh, so I thought that I will speak on foundation of quantum mechanics, and indeed I am going to speak on foundation of quantum mechanics. But Arun suggested that why don't you put this title, historical developments of quantum mechanics. Historical, if we want to discuss historical actual historical development of quantum mechanics, that will be a little bit big subject. It needs so many hours. But I will concentrate on fundamental things, which actually gave rise to the subject that some of you are doing your research, this quantum information theory, and some application of foundation of quantum mechanics. So let us go straight to the subject. So Heisenberg, in 1925, he actually discovered quantum mechanics in some sense, that he was very ill and he went to Iceland. He was there and he was thinking about spectrum analysis of an anisotropic harmonic oscillator. Then he found that Bohr's theory cannot explain everything. Then suddenly, somehow, he got the idea that when you are dealing with micro world, then if you consider position and momentum, they are not just numbers. They will be arrays of numbers. And he was thinking that the arrays will be such that if you take position for this microparticle and momentum for this microparticle and take their representation, their multiplication may not be commutative. That means PQ may not be equal to QP. It suddenly came to his mind, but still he did not know what kind of mathematical object it is. He could not understand at that time because he didn't know matrix. Then some of maybe Pauli or Max Born, they actually told that it is indeed matrix. And the equation powerful, which we use whenever we do quantum mechanics. This Q is an operator, which is position operator. P is another operator or momentum operator. And this QP minus PQ, it is not equal to 0, but it is proportional to identity. So this was a big discovery, but still people could not understand around that time. Suddenly, Schrödinger in 1926, he told that microparticle or microwall should be represented by wave, and he wrote a wave equation. This H means some Hamiltonian acting on the system. H psi is equal to IH del psi del T. So, and physicists were more akin to this solving this differential equation, and immediately they could solve so many problems like harmonic oscillator, hydrogen atom problem, and they get energy eigenvalues, and they could explain so many things. So at some point of time, Heisenberg was thinking that his fate is doomed because everyone is accepting Schrödinger, not Heisenberg. But somehow in 1926 itself, Schrödinger proved that his formalism and Heisenberg's formalism, though it is little bit obscured, but they are actually equivalent mathematically. That Ranada can speak to you that actually there are two Hilbert space. One is a small L2, another is big L2, and they are actually isomorphic. This is the thing that Schrödinger could solve. Then Max Born in 1926, wave function was there, but what is the meaning of the wave function? Schrödinger had something in his mind that at some point of time he was thinking wave only exists, there is no particle. But finally, Max Born told that no, meaning of this thing that if you perform the position measurement, then probability of finding this particle upon the measurement, probability of getting the particle in the set X is given by this quantity. Take mod of psi x squared, then integrate over x, this region you will get, but you should be very careful upon measurement. If you perform the measurement, the probability of getting the particle inside the, sorry, how it came? How it came last? Yeah. So you have to be very careful that upon measurement, the probability of getting the particle inside this site X is given by this quantity, and it was introduced by Born, but it has been generalized for other observable also. And Heisenberg in 1927, that is famous. Actually, many people understand quantum mechanics by this expression. Delta X into delta P is greater than or equal to H cos by 2. So what Heisenberg wanted to tell, that joint measurement of position and momentum is possible if you allow some errors. Errors in position measurement, errors in measurement, and if they satisfy this condition, error of x into error of p is greater than equal to some quantity h cut by 2, then only joint measurement is possible. That's why it also tells that perfect joint measurement of position and momentum is not possible, but Heisenberg could not prove this thing. Even Heisenberg could not prove this relation itself properly. He gave some ideas like gamma ray experiment, in terms of gamma ray experiment, where he wanted to tell that if you try to look at the particle position very very correctly, then you have to use high power, high frequency light like gamma rays, but it will change the momentum discontinuously. And in that way, he derived something, but which is not exactly this thing. But he emphasized always that joint position and momentum measurement is not possible if you don't allow certain errors which satisfy this condition. Then Bohr in 1927, he introduced the idea of complementarity. This is for many years, this was not well understood because Bohr used to speak in a very complex way. But now we understand things that wave feature and particle feature cannot be observed simultaneously. Like if you send photon one by one into this interferometric setup, in this interferometric setup, then actually if you send 1,000 photons, 50%, because this is 50% beam splitter and photon is indivisible. When you try to detect the photon, if there is two detector and there is one photon, then only one detector will click, other detector will not click. Photon is indivisible when you try to detect it. The argument will tell you, classical argument will tell you that if you send photon one by one, this is 50% beam splitter, this is 50% beam splitter, then half of the photon should go here and half of the photon should go there. But in actual experiment, it may happen that no photon go to D1, all photon goes to D2, and you cannot explain this thing by classical way, by assuming that photon is indivisible. Photon is indivisible, it is true. When you perform the measurement and there is single photon, if this photon is in this room, then it is not in the other room. It behaves that way. But when you don't look at it, you don't know which path it is taking. But photon is very clever also. If you try to put a detector here to learn which path photon has taken, then photon is so clever, it will destroy the interference pattern and 50% will go to D1 and 50% will go to E2. So it is very clever particle. If you try to detect it, if you try to know, let me see which way photon took, between these two paths, which one photon take, if you try to detect it, then photon is so clever, it will behave like a classical particle. And this is one statement of that wave feature and particle feature cannot be verified simultaneously. There is another thing which Bohr could not establish by mathematics, but could understand that position and momentum measurement is not possible. So now we can express it mathematically. If we find some instrument to detect the particle in the set X and another instrument which detect the particle in the momentum interval Y, then these two experimental setup are mutually exclusive. They cannot be performed simultaneously. But at the time of Bohr, this could not. This was proved around 1950s. But still, for clear understanding, it took some more years. Maybe in 70s, it was clearly understood that perfect position and momentum measurement is not. Then finally, Copenhagen interpretation is there. So it tells that microparticle possess pre-existing properties. Like when we measure our temperature by a thermometer, do we think that measurement creates our temperature? We don't think. We think it. Or if we measure height of something, do we think that measuring rod creates height? We don't think. Height was already there. We reveal it through our instrument. But Copenhagen interpretation is telling something else. Microparticle does not possess pre-existing properties to be revealed in future measurement. The act of measurement creates some result. This is very, very different from our classical intuition. That means if you don't measure the particle, then you cannot tell it is somewhere. You may not know, but you can think it is somewhere. You cannot think in this way in quantum mechanics. If you perform the measurement, then quantum mechanics can tell with certain probability you will get the particle in this region. At most that you can tell. And probability can be inferred from Bond's rule. Discontinuous jump of a state occurs due to measurement. This is again very controversial thing. This collapse postulate. It is postulate that after the measurement, it irreversibly changes to a different state. And there had been a long debate between this Bohr camp. In Bohr camp, there are so many great people like Heisenberg, Pauli, Max Born, Jordan, so many people. But Einstein, to some extent, was alone. In 1927, there is what conference it is called? Solvay conference. Solvay conference, they had big debate. And Einstein in 1927 first tried to refute the impossibility of joint measurement of position and momentum. So Heisenberg or Bohr was trying to tell that perfect position and momentum measurement is not possible. But Einstein to create a situation, create a thought experiment where he wanted to show that position and momentum can be perfectly measured jointly, but he failed. He also tried to establish non-local feature of quantum mechanics by using collapse, but never found contradiction with principle of relativity. Einstein was thinking that it may quantum mechanical collapse postulate may somehow contradicts relativity, but he could not establish that thing. But Einstein never accepted the position that particle cannot have definite values of position and momentum. That Einstein never believed. And also quantum mechanics was the people who used to believe this first one, they also could not prove that single particle cannot have definite value of position and momentum. Quantum interpretation is one thing, but to establish that thing is different thing. So, at least at this point, Einstein at that time could not be challenged. Uncertainty principle, once again, what is meant by this thing? Statement of uncertainty principle, many actually. It is impossible to prepare a state in which both position and momentum are arbitrarily well localized. It is called preparation uncertainty principle. Actually, in 1927 itself, possibly Kennard proved this mathematically. And after that, Robertson proved it, and then so many people, actually in India, Sitaram and Tangabelu, they also proved this thing. And recently, Orun and McCone, they proved this kind of uncertainty, preparation uncertainty relation, but it is not product. For their case is sum of these two terms. And they have given a bound also. But all of them are preparation uncertainty principle. Next statement, it is impossible to measure position and momentum simultaneously. This is called measurement uncertainty. Actually, full statement should be like this, that as I told, that if you don't allow any error, then perfect position momentum joint measurement is not possible. If you allow the error that we are discussing, then it may be possible. And there is a third statement, it is impossible to measure position with, I have written something wrong. It is impossible to measure position without disturbing momentum. It should be, a perfect statement should be like this. And impossibility of joint measurement, as I told that this is projection operator. I'm not going into the mathematical detail. It tells that the observable which will represent perfect joint measurement of position and momentum is trivially zero. That means it does not exist for bounded x and y. And in search of joint measurement, what we have to do to have bad observable. How to make bad observable? So what you do, you take projection operator and give a weight function like this. Sorry. Yeah. You give a weight function like this, fx, which is the probability function, and this f actually take care of the error in the position measurement. Similarly, you create another operator, which you start from a projection operator, give different weight, and you create another positive operator where gy is again a probability kind of function, and then you can construct I'm not going into details. Then you can construct a function like this, construct a positive operator like this, whose marginal will be position measurement whose marginal will be momentum measurement. So they are represented by this quantity. This quantity. I have never used this thing, that's the problem. This is the observable, and if you take marginal, marginal means one of them you make it whole real line, then you get the marginal observable, and this marginal observable is actually unsharp count of perfect position measurement, and perfect momentum measurement, which is unsharp counterpart. And this unsharp counterpart, this unsharpness is taken care by this function f and g. If they are delta function, then it is perfect joint, perfect measurement. And now if you calculate the variance of x and variance of p, what you do in your standard quantum mechanics, then actually you will get, generally you get these two terms for some quantum state phi, but for this case you will get another extra term, which is dependent on f and g, and this is contribution due to unsharpness. That means you have introduced error, and that error is taken care of by this variance quantity. And it has been shown, it has been recently proved by Paul Bush, Lathi, and Warner, finally, that you can have a uncertainty relation like this. That means error due to position measurement, which is represented by AF, and error due to error for the momentum measurement, which is represented by function G. And if you calculate these two quantity, then it satisfies Heisenberg uncertainty relation, which Heisenberg could not derive that time because mathematics was not that much developed. And in the actual situation, this variance of X and variance of G, actually they are related to the initial state of the apparatus. When you are measuring a quantum observable, you have an apparatus, and the apparatus has an initial state, and on all of them you are applying some unitary operator. This measurement error, they are related actually to the initial state of the apparatus state, and this was explicitly shown by Arthur Kelly in 1965 and Paul Bush in 1982. So this is an interaction Hamiltonian, and this is the system of the state of the system. This is a state of the first apparatus, which measures the position of the particle. This is a state of the second apparatus, which measures the momentum of the particle. And if you employ these whole things, then finally you will get, because then this position error contribution will come from both phi 1 and phi 2, which are initial state of the apparatus. So it also proved that Heisenberg told that position measurement disturb momentum, or momentum measurement disturb position. That is also established by this relation. And finally we'll get this quantity, which is told as Heisenberg relation. So total error, this uncertainty in observable, plus another term comes, disturbance due to measurement of conjugate observable. Position and momentum, they are conjugate observable, they are Fourierly connected, and so if you try to measure one of them, others are disturbed. But what I am trying to tell all this thing, I am trying to tell all this thing because people are trying to understand what is meant by uncertainty principle. And to do that, they actually came to the idea of unsharp measurement. But that is not the most important thing. Most important thing is that they came to the conclusion that projective measurement is not the only measurement. Most general measurement in quantum mechanics is given by positive operator valued measure. That means you take positive operator if the sum is one identity, then it is actually a measurement. And even in d-dimensional space, there may be, if you consider a d-dimensional space, and if you consider a standard measurement, then actually there may be at most d number of projectors, d number of orthogonal projectors. But come to the most general idea of measurement, then there is no bound. Here there is no bound. Even on a qubit, you can perform a measurement whose outcome may be 100 or 200 or 300. And Bond rule is given by the same kind of equation. The state is rho, then probability of getting the ith result is given by this quantity. And actually it has been shown that this Neumark dilation theorem, that actually this measurement is actually projective measurement but on a higher dimensional Hilbert space. That means you have to take the system and ancilla, their dimension will be higher, and you can realize this POVM measurement as a projective measurement on that higher dimensional Hilbert space. This was a big development. Other big development that took place in around 1970s, or I can tell 60s. Actually, Sudarshan started this thing. Sudarshan actually found this formula that most general quantum operation is given by this kind of thing, but he made some mistake. Finally, Krauss in 1971, 72, 73, he published many papers, and finally we get most general quantum operation. Generally, by quantum operation we mean unitary operator, but most general quantum operation is represented by, mathematically you can tell it, trace preserving completely positive map, and that is given by this kind of quantity where FIs are operators satisfying these two quantities. Here I am wrong. This is not there. Fi dagger Fi summation over I is equal to identity. Somehow I don't know how it came. It need not be positive. These FIs are need not. I wrote it wrongly. Or it can be represented as unitary operator, but on a bigger system, then you trace out the or ignore the extra system. Then you get the completely positive map. And these two development contributed in a big way for the development of quantum information. These people discovered no cloning theorem, who discovered no deleting theorem. But now, because of this development, you can tell with what is the highest fidelity that with which you can clone a particle, or with what is the highest fidelity of deleting. That thing you can calculate, because now you don't about most general quantum operation. So many things you can calculate, and you can think this is the highest in quantum mechanics because of this development. Now I am going to a different direction, which is more or less foundation. Which one is later? Yes. Yeah. Actually, many people know quantum mechanics in terms of Heisenberg uncertainty principle. Next thing is EPR. Many people have heard about EPR, but sometimes they will think that EPR is such kind of thing that if you do something on this particle, something will happen to the other particle. This kind of concept is there in general. But Einstein actually in 1935, he wanted to tell that if it is true that nature respects this condition of locality and condition of reality. Locality means if there are two particles, however they are correlated, but do something on this particle, it will not immediately influence the other particles. And reality means without disturbing the system, you can predict the results, then you can tell that there is a corresponding reality for that observable. If you assume these two things, then using some argument, using some maximally entangled state, sometimes called singlet state, 1 by root 2, 0, 1 minus 1, 0, this kind of a state, you can argue that sigma z and sigma z both are real for this pair of particles. But if you look at quantum mechanics sigma x and sigma z don't commute, then there is no eigenstate, common eigenstate for sigma z and sigma x. So there is no quantum state for which sigma z and sigma s both can be real. So Einstein told that, but my argument is telling that it is possible. Then of course I am not telling quantum mechanics is wrong. Quantum mechanics is inconsistent. But he told or he tried to prove that quantum mechanics is incomplete. Remember that telling one thing incomplete is not equivalent to telling that it is wrong or it is inconsistent. Einstein finally came to the maybe for some time Einstein was thinking that quantum mechanics will have some contradiction with relativity, and he will prove that, and then finally will tell that quantum mechanics must be wrong. He might have this thing in his mind for some time, but finally in 1934 he could only establish, or he could try to establish, that quantum mechanics is incomplete. But in 1932, which Einstein possibly didn't see, those at some point they were both in Princeton, I think. No, they both were in Princeton. One year. But I think the Einstein never looked at this mathematical theorem, or Einstein might have thought that a mathematician has nothing to do with a deep question of quantum mechanics. But somehow von Neumann gave a proof in his book published in 1932. The name of the book is Mathematical Foundation of Quantum Mechanics. Here he gave a, I don't know what to tell, but the statement of the theorem is something like this. He is taking a Hilbert space, then he is considering an expectation value. Of course, from quantum mechanics, expectation value comes. You can calculate if you know psi and some observable, you can immediately calculate the expectation value, psi a psi. But he is not that. He is considering that. Sorry. Or I can switch it off full. He is considered a expectation functional, not considering the quantum one. General expectational functional, which will satisfy these three things, that A is self-adjoint. For if you take a collection of self-adjoint operator and you consider a real number, then it forms a vector space. Now, if you consider any self-adjoint operator, this expectational functional, yeah, it is real. If you take any Hermitian operator, for that Hermitian operator, this value of E is real. Because in quantum mechanics also psi a psi, if A is a self-adjoint, it is always real. If you consider two observable A and B, then A plus B is also a self-Hermitian operator, no? Then expectation on this E A plus B is equal to EA plus EB. Again, it is satisfied by quantum mechanics. If you take psi AB psi is equal to psi A psi plus psi B psi. But now he is telling that he is putting this condition not on the quantum expectational functional. He is telling that every theory should satisfy this condition. And third thing on identity is it is not, again I have made a mistake. It is identity operator, it is one. Then he could prove that these expectations, there is always a density matrix such that every expectational functional can be found from a density matrix. It is a very powerful statement. It is trying that there is no other state other than quantum mechanics. Even if you start from a more general consideration, finally you get only density matrix. That means quantum state. So there is no other state. It is very, very powerful. It immediately disproves Einstein. Einstein believes that observable may have definite values for the particle. But this theorem will tell no, whatever state you consider, it will be finally a density matrix, and for every density matrix, always you get a observable whose probability of or whose what should I tell? Whose which will not have definite value for that state. Like if you consider sigma z, and if you take the case 0, then sigma z has a definite value, but sigma x has no definite value. Similarly, if you take eigenstate of sigma x has definite value, but sigma z doesn't have definite value. And if you consider any state, I can always find a observable for which it has no definite value. That means having definite value is not possible in the world, as if von Neumann has discovered. Because every state is finally a density matrix according to his theorem. So dispersion-free state, dispersion-free theory may not be possible. But David Bohm in 1952, this theory first developed by de Broglie, but somehow that time in 1927 it was rejected. But the same de Broglie theory was used by Bohm, and he actually could show that there is an alternative theory where every observable has a definite value, still it reproduces quantum mechanics. For this thing, he told that actual state is not just psi there, but it is like Einstein. Einstein is telling that quantum mechanics is not complete. If quantum mechanics is not complete, so there is psi. Maybe it completed by taking some another variable which is missing. And in Bohm's theory, actually, you see, he is telling that actual state is psi along with the particle position. We may not know it, but there is a position for the particle. And probability of that particle at this position is given by this same quantity. And he gave two equations. One equation is Schrodinger equation, another equation that wave guides the particle where to go. So particle is there, wave is, it is like electromagnetic wave. So electromagnetic wave decides where the particle will move. Here this psi wave will decide where the particle will move. And by this theory, he can tell that every observable has a definite value if you give the full description of the measurement apparatus. Then this theory can tell that if you measure momentum, you will get that value, this value. If you measure momentum, you will get this value. But full description of the measurement has to be. That means initial state of the apparatus has to be given, what kind of unitary measurement you are going, that has to be given, and full description of the actual state has to be given. Not only psi, as well as psi and x. But these two contradicts. Von Neumann is telling impossible, David Bohm is telling impossible. And actually, with this contradiction in mind, John S. Bell was thinking deep about quantum mechanics. And finally, he could make the breakthrough. Arun, I cannot handle this thing properly. Yeah. But I wish to tell another thing. Another important deep theorem was discovered in 1957, where actually, if you take a Hilbert space and take the collection of all projection operators, and you know that if you take the expectation value of projector, it is actually indeed probability. So if you take a Hilbert space and consider collection of all projection operator, of course, projection operator does not form a vector space. At most, it can produce a orthomodular lattice. That's why it is very difficult to prove this theorem. So you consider a probability measure on this projector. Means if P is a projector, then mu P is less than or equal to 0. If you take collection of orthogonal projectors, then mu of summation over P is equal to summation over mu Pi. It is like Kolmogorov, but for orthogonal set. Kolmogorov axiom, but for orthogonal projection operators. And on identity is equal to 1, then if the dimension of the Hilbert space is greater than or equal to 3, 2 is excluded. Then for every probability measure, there is a density operator. Then by density operator, I mean quantum state, which is Hermitian, positive, and stress is 1. And pure state psi is nothing but extreme density matrix, like rho square is equal to, if rho square is equal to rho, then for every rho there is a psi. So this was a very powerful theorem, and this has no flaws actually. And then with all this thing, Bell was thinking, what is the matter? There is von Neumann theorem, there is David model, and there is again Gleason's theorem, which is of course little bit liberal that it did not include two-dimensional Hilbert space. Bell in 1964 to 66, Bell showed the von Neumann proof is not tenable. Actually, he called it silly. Gleason's theorem shows that a class of hidden variable theory is incompatible with quantum, showing quantum mechanics is contextual. That means Gleason's theorem show that, so Einstein told that quantum mechanics is incomplete. Then if quantum mechanics has to be completed, then certain hidden variable has to bring in. This kind of theory still may go on, but Gleason's theorem shows that not all possible hidden variable theory is possible. A class of hidden variable theory will be impossible. At most, the Gleason's theorem can tell this thing. What is this thing I am going to tell? Finally, Bell could show that quantum mechanics is incompatible to local realism propounded by Einstein. This is very profound, and this is the most fundamental. Some people tell that this is the most fundamental discovery of science in 20th century. I don't fully agree with this thing, but it must be one of the most profound discovery of science in 20th century. Actually, just to disprove von Neumann, I am not discussing von Neumann's. I'm not discussing von Neumann's fault, but von Neumann's fault is a very trivial kind of fault. So if you take fx dx is equal to 0, von Neumann come into the consideration that fx is equal to 0. Integration of fx dx is equal to 0. Can you conclude that fx is equal to 0? Von Neumann did this thing. But it occurred in such a way that he could not recover it, but it is that kind of mistake. This is quantum thing, that if quantum state is this thing that been polarized along some direction n, and if you perform the measurement of spin along some direction m, then probability of getting up result is half 1 plus m dot n, 1 plus n dot m. So this is very good thing. Scalar product in ordinary R3, and probability of minus sign is half 1 minus n dot m, or if you calculate the average, it is n dot m. N is the state direction of the state polarization, and m is direction of measurement of the polarization. So this is very good function. No? What Bell could do, Bell told that von Neumann theory must be wrong because I construct one counter example. And actual counter example I have not going, but there is more simpler counter example. Actually, Bell told that completed state can be taken psi and some scalar. Psi means it is because every qubit state can be seen as a vector in the Bloch pair. So let psi is corresponds to this direction n, and lambda is just a scalar quantity which can take value from minus up to plus up and with equal probability. So lambda varies from minus up to plus up, and he gave a prescription for definite value. If n is my state, m is my measurement direction, then this is the rule, which is always either plus 1 or minus 1. Because the sine function is plus 1 when x is greater than or equal to 0, it is equal to minus 1 when x is strictly less than 0. So he gives a prescription that whatever state is there, whatever measurement is there, I will get. Quantum mechanics cannot give definite value, because quantum mechanics can give definite value only when it is in one of the eigenstate. But here the prescription is that for every state and for every observable, he will give a definite value, which can be either +1 or -1. And how do you go get quantum result? You integrate it over d lambda rho lambda, because lambda is hidden variable, so you have to integrate over it and finally get the quantum thing, and exactly you will get the quantum thing. So believing that every individual particle has a definite value for every spin, this thinking cannot be challenged. Because if someone thinks in this way that every individual particle has definite spin for all over all direction, still you can reproduce quantum mechanics. Then how quantum mechanics can challenge your model? Because it finally reproduces quantum mechanics when you integrate over this hidden variable, which is in this particular case, it is a scalar. And not only that, after that in 1967, 67 Kochen and Speger, they provide another model where both are vector. The state is represented by n and another unit vector lambda. And earlier case it was a scalar, here it is a unit vector. And by that thing, again you can construct a model where every spin will have definite value, but finally it will reproduce quantum mechanics. So there are two models. In one model, here model is very peculiar. Here the value given to the observable does not depend on the, it is fully dependent on lambda, and quantum state is nothing but probability distribution over this hidden variable. But anyway, we are not going much in this direction. Yeah. Now we'll see the consequence of Gleason's theorem. So if you take sum of orthogonal projections, as I told you, then it constitutes a measurement. Now, if you consider three-dimensional Hilbert space, then phi 1, phi 2, phi 3, they are an orthogonal set. But you can consider another projective measurement where it is phi 1, phi 1, phi 2 plus phi 3 by root 2 and phi 2 minus phi 3 by root 2. These also constitute an orthogonal basis. Phi 1, phi 2, phi 3 forms an orthogonal basis, but this phi 1, 1 by root 2, phi 2 plus phi 3 and 1 by root 2, phi 2 minus phi 3, this also forms an orthogonal basis. So now in hidden variable theory, you assign definite value to a projector, which can be either 1 or 0. To give definite value to a Hermitian operator is equivalent to assigning 0 or 1 to a projector. And of course, if they are mutually orthogonal, if you consider this projector P1, P2, P3, then one of them will get 1 and other projector will get value equal to 0 because they are mutually exclusive. At the same time, spin value cannot be both up and both down. This cannot happen. Now, but measurement in this basis and measurement in this basis, they are different kind of measurement because they don't commute. But phi 1 is common. Phi 1 is common. Now, question is, if my hidden variable theory gives definite value to a projector, which can be either 1 or 0, then I have to answer further question that will it consider whether phi 1 belongs to this set or phi 1 belongs to that set? In two dimension, this question didn't arise. In two dimension, if you consider a vector, then its orthogonal vector is unique. But in three dimension, if you consider a vector, then another two orthogonal vector, they are not unique. in the plane, it can be chosen in so many ways. So hidden variable theory has to answer further question that if in this measurement it gives value 0 to this thing, will it give value 0 to this phi 1 when you consider this measurement, which is a different measurement? This question has to be answered, which was not raised in two-dimensional Hilbert space. And this is called, now you have to take a position. If you, yeah, for every projector, whether it belongs to this set or that set, I will give one value, either 0 or 1. Then it is called non-contextual hidden variable theory. And Bell could prove that non-contextual hidden variable theory cannot reproduce quantum mechanics. And that can be shown in a very, actually, Kochen and Specker in 1967, they used 117 projectors to prove this thing. But now we are lucky. Cabell in 1996. Using fourth dimension, he could show that there are 18 projectors using which you can prove that quantum mechanics is incompatible to non-contextual hidden variable theory. This proof is very simple. Yeah, you take normalized 18 vectors. 18 vectors in fourth dimension, and you can have 9 group of orthogonal bases. And the rule of value assignment that every projector you give a value which can be either 0 or 1. For simplicity, this is actually projector, this is vector. I have written, for simplicity, I have written this small term. And sum of them should be equal to 1. Because it is mutually exclusive event. So if you give it one of them to 1, then the value that you assign to other projector should be 0. So sum will be equal to 1. Yeah. It is non-contextual. Why? Phi 1 appears in this basis, phi 1 appears also in this basis. Similarly, every vector has appeared twice. And value can be either 0 or 1. Now, can it be consistent? There are 9 equations. If you add them, right hand side will be 9. Left hand side, every vector has appeared twice, and the value can be either 0 or 1. So, left hand side will be, any student, even or odd? Left hand side, every quantity has appeared twice, and value can be either 0 or 1. So, left hand side will be even or odd? Even. And right hand side is odd. So, you cannot consistently assign definite values. But if you tell, no, my theory will give this phi 1 a value which may be different when the same phi 1 is appearing in a different measurement, then it becomes contextual theory. That contextual theory may reproduce quantum mechanics, but non-contextual theory cannot reproduce quantum mechanics. This is the idea. There was a big discovery. And finally, so how much time I should take? 10 minutes. Yeah, can I have some water for drink? Let me continue. Bell proved that if you take Einstein's conception about reality and locality as true, nature obeys this locality and reality, then Bell showed that a inequality is satisfied. An inequality is satisfied by the statistics from a theory which obeys Einstein's locality and reality concept. And here I could have given a very simple proof. If you assume two particles, one side you can measure x1 and x2, other side you can measure y1 and y2, but the value of measurement is always +1 or -1. If you assume this thing, then you can derive a quantity which will come, but that is a very strong assumption. Observable has definite value for both particle and locality. That means once you give the value, choice of measurement on the other side will not influence that value. Then it is very simple to deduce Bell's inequality, but I have taken a little bit more generalization of this thing. I am saying that if you consider this probability, P result X on this side, I have made a mistake again. So what you have to maybe I have confused between X by X. I tried to consider that they are input or measurement, and by A and B output. Somehow I might have confused some in some places. So it should be actually PAB XY lambda. But interesting thing that probability factorizes. This is Bell locality condition. Actually, Bell locality condition was derived to be equivalent to two conditions. One is parameter independence condition, which is equivalent to no signaling condition, and outcome independence condition by Jarrett, possibly in 1982. So this is called Bell locality condition. That means probability on this side and probability of getting result on the other side, they factorize. But in general, it may not factorize. But Bell is considering, we consider at the hidden level, it factorizes. This is the assumption. That means they don't influence. If you consider that probability factorizes in this form, that is called Bell locality condition, then I am not going in details, but you can calculate this quantity. No, sorry. X1, Y1, average of X1, Y1, average of X1, Y2, X2, Y1. Again, I have made a mistake. Here there will be a minus sign. This is bounded, this mod of this quantity should be bounded by 2. This is Bell's inequality. And it has been shown that quantum mechanics is incompatible with local realistic theory because you can prepare two particles in such a state and you can choose two measurement on this side, two measurement on the other side, and collect the statistics and could show that this is not true. This quantity can reach up to 2 root 2, which is much higher than 2. So again, this is a discovery that Einstein used to think that nature behaves locally and in the realistic way, but you could show that no, Einstein was not correct in thinking. Quantum mechanics is indeed has contradiction with local realistic theory. We can nowadays in foundation finds application in quantum information theory. So you can represent it in a different way. Sometimes I like to tell this thing. So there is two rooms, one is in Alice and the other is in Bob, and there is a game that they will be given question. Alice will be asked two questions, A1 or A2. Bob will be asked two questions, which can be either B1 and B2, and they will be asked this question randomly from this set. But answer can be only +1 and -1. for both all the question. Answer can be only +1 or -1. But there is one condition that after the game starts, they cannot make phone call. That means if Alice gets A1, Alice does not know which question has gone to Bob. Similarly for Bob. And so how many possible set of questions are there? 4. A1, B1, A1, B2, A2, B1, A2, B2. And this will come with 1/4 probability. All the question will come with 1/4 probability. So they will not be allowed to communicate. So this question will be asked and answer will be collected. 1,000 times it will be repeated. Finally, all the answer will be taken in a room and will be checked whether they satisfy this condition. For A1, B1, their answer, product of their answer has to be +1. For all 3 pairs, product of the answer has to be +1. But for the last pair, A2, B2, when this fellow gets A2, this fellow gets B2, in all those cases, their product of their answer has to be -1. What do you think? Can it be done? Can there be a strategy by which they can win this game? You can think, but I don't know whether I have given a proof. Possibly I have not given a proof. So what do you think? This game can be won? Let me tell. Just for every question they will answer, their answer will be +1. Then in how many cases they will be successful? How many cases? 3/4. 75%. But immediately we are not getting any strategy by which they can win with 100% probability, no? But what do you think? Will they? Because if they design some answer, because Alice's answer cannot be function of Bob's question. Similarly, Bob's answer cannot be function of Alice's question. So you have to give 2 answer and 2 answer on for both. I mean, if you fix the answer on both sides, then they have to satisfy for these 4 equations. And these 4 equations, again, the same problem. If you take the product of them, right hand side it will be -1, but left hand side every answer has come twice. So equation is positive, so it will not be possible. But your intuition is correct. We'll prove that 75% is the best, beyond which you cannot go. So you start with Bell's inequality. And after some manipulation, you can prove that probability of winning this game is bounded by 3/4. This is nothing but you are expressing this thing, average of AI Bj is equal to probability of that their value is equal minus probability that their value is unequal. Because when unequal product is -1, and when equal their product is, if both are -1, then also product is +1. When both are +1, then also product is +1. So in this way you can calculate the average. And probability satisfies this normalization condition, using which you can calculate the probability of winning the game by local realistic theory. Because this is true for local realistic theory. So using local realistic correlation, the highest probability with which you can answer correctly is 3/4. But in quantum mechanics, you can choose a state and you can choose measurement. For 2 questions, you will choose 2 measurements. Similarly, other will choose for 2 questions, will choose 2 measurements. And if their spin result is up, they will answer +1. If their spin result is minus, they will answer -1. In this way, they can win this game for quantum mechanics, which is 85%. More than 10, it is 10% more, but it is not 1. And it is true that quantum mechanics can never go to 1. But you may not be satisfied with just 10% more than what local realistic theory allows. But nature has given this condition. You cannot go beyond. With 3 particles, which I have not discussed, there is a similar kind of game with 3 qubits, where you can win this game with 100% probability. And maybe Pankaj has done many works on this, many particle non-locality. Again, I am not going to discuss this thing. This is a very big discovery, that kind of model, quotient model discovered in 1967, where quantum state is not part of the reality. Quantum state is probability distribution over the reality. That kind of theory has been rejected. This is a big discovery in possibly 1910. No? This no, PBR. 2010 it will be. Because 2011, there was a conference in your place. There we discussed this thing. But I am not going to discuss this thing. This is a very big discovery. Yeah. But now we derive Bell's inequality with the assumption for underlying theory, because we are telling there is some hidden variable theory we don't know, but it is there. This is actually giving definite value to all particles. That means our operational theory is quantum mechanics, but we are telling this is quantum mechanics, but underlying there is a theory where things are definite. But when you come to the quantum level, after integrating over this hidden variable, you get quantum mechanics, which is a probabilistic theory. We are thinking in this way. But if you take operational theory itself, that means operational theory means you do you experiment in lab, and based on that you construct a theory. Quantum mechanics is such a theory. You have this result, that result, then accumulating all this result, you construct a mathematical theory, which is the operational theory. Now, question is whether Bell's inequality can be derived by doing some assumption on the operational theory, not under the hidden variable theory. This is also true. If you consider no signaling condition, so first assumption is you assume that operational theory is predictable. Predictable means probability will be either 0 or 1. That means predictable. Second thing, we assume no signaling. No signaling means you perform some measurement and get a value. Probability of that thing should not depend what measurement has been chosen to a distant particle. In whichever way they are correlated, but my measurement probability of a result of a measurement on this particle should not be influenced by choice of some other measurement on the other particle. This is no signaling. If you assume these two conditions, then again it implies no violation of Bell's inequality. If now quantum mechanics satisfies this condition, quantum mechanics is indeed a no signaling theory. Quantum mechanics does not allow superluminal signaling. Then if Bell's inequality is violated, then what condition should be violated? Predictability. That means practically, if a theory violates Bell's inequality, then you have randomness. Because having hidden variable theory and having definite value, that is the imagination that whether in principle that kind of theory can be constructed. But here we are dealing with the theory itself. Theory, I mean operational theory itself. And under that operational, you have assumed these two conditions, then Bell's inequality should be satisfied, but in reality Bell's inequality is violated. This tells that your theory, quantum theory is not predictable, we know. But someone may tell that no, some other theory can be constructed obeying no signaling condition, which is predictable. But if violation of Bell's inequality is there, then it is not predictable. That means there will be some probability which will be neither 0 nor 1. That means you get randomness. And interestingly, If Bell's inequality is violated, then how many observables are involved in violation of Bell's inequality? You know it. How many observables are involved in violation of Bell's inequality? 2 on this side, on the other 4. You can calculate any one of them. If Bell's inequality is violated, then predictable means probability is close to 1 or 0. And randomness means probability is more close to half. This is the value, and actually, if you calculate this quantity, 20% device independent randomness you get. That means you cannot go be. So 4 observables are there. For if you consider 1 observable, probability of getting up and probability of going down, it will be 20-80%. You cannot go 10-90 or 5-95. So it is not fully random, but 20-80, below 20-80 you cannot go. At least 20-80 randomness you have to allow to have violation of Bell's inequality by the amount to √2. But in quantum mechanics, actually, you know how do you get Bell violation? Quantum mechanics, how do you get violation? You get an entangled state, you have observable, you measure them and find the calculability, it becomes 2√2. Can you tell me what is the randomness for quantum mechanics? For maximally entangled state? For maximally entangled state, what is the density matrix of the subsystem? Identity by 2. So every observable will be completely random. So in quantum mechanics, every observable for maximally entangled state is completely random. But here we are guaranteeing randomness not from quantum mechanics. By believing quantum mechanics, we are telling we believe no signaling. And under no signaling, still you are getting randomness. That is important. Device independent randomness. You are getting randomness not from a particular theory. You are having a statistics, that statistics violates Bell's inequality. You have no signaling principle. Under that no signaling principle, just from the statistics you can tell that there is randomness. That randomness is not full, is not half, but still it is random, 20-80. And randomness can be amplified. If you have 20-80 randomness, you can go up to 50-50. Because randomness can be amplified. Von Neumann first proved it. You take 2 biased coin and toss both the coin. From that thing, you reject some of the result, you get complete full randomness. You can amplify. But here, not from a particular physical theory, but from a principle, you can assure randomness. That means it is device independent randomness. You don't, you collect the statistics, you don't believe the device, you don't believe in quantum mechanics even. But if you get these statistics, if the violates Bell's inequality by this amount, you can tell at least this much randomness is there. This is very, very powerful result. And I'm not going to discuss in detail, but let me tell you, for Bell's inequality violation, you have considered 2 measurements this side, 2 measurements this side. But Pottis, Boss, Brownstein, they discovered a inequality, a different kind of Bell's inequality, which is called chain Bell's inequality. Am I correct? And it involves large number of observable here, large number of observable here. By that thing, they actually designed another inequality, and violation of which imply that Even under no signaling condition, randomness is completely like quantum mechanics. If it is in quantum mechanics, it is probability of getting up is half and probability of getting down is also half. Even under no signaling condition, you will get the same thing, but you have to pay the price. You have considered almost infinite number of measurement on this side, infinite number of measurement on the other side, have so many terms in the inequality, but if that inequality is violated, it is assured that you have got complete randomness. Under the condition of no signaling, you need not care about quantum mechanics. But you have to sacrifice, not only with 4 observable, but almost large number of measurement on this side, large measurement on this side. This was discovered by Kolbach and Renner in PRL 2008. Then it was nicely written by Leifer 2014. Just let me finish. Violation of Bell's inequality by quantum mechanics needs addressing individual quantum system. Actually, all this no cloning, no deleting, and all these ideas came because after this Bell's inequality, to establish that Bell's inequality is violated in laboratory. That means they are trying to address the individual particle. And when the question of addressing individual particle came, then some started thinking manipulation in a theoretical sense, whether it can be cloned, whether it can be deleted, whether it can be done something else, like that. The concept of manipulation of individual quantum system gave birth to quantum information theory. And most general quantum evolution and POVM, that means most general observable, enriched and continue to enrich quantum information theory and foundation of quantum mechanics. The Bell non-locality enriched the quantum information theory in a different way that I was trying to emphasize. For example, device-independent key distribution. The earlier result also implies device-independent key distribution, which needs some time to explain. So maybe later, if we get chance, we will discuss it in details. And device-independent random number generation. So today, somehow quantum information theory is enriching quantum foundation of quantum mechanics. On the other hand, some discovery in foundation of quantum mechanics is enriching quantum information theory. In this way, they are cooperating each other, sometimes competing with each other. Yeah, that's all I have to tell.
Okay, so thanks, Professor Prasad, for this wonderful and insightful talk. And now we open for
when you are discussing the hidden variable,
Yeah.
From two dimension to 3 dimension.
Yeah.
So you had this one axis, the other one is of course basis vectors are rotating in this plane.
For 3 dimension.
3 dimension. Then you ask the question: is the hidden variable theory, whether this phi1, this measurement will remain the same?
No, I am asking that full measurement means complete orthonormal basis. But this, if you choose the phi 1, then still other 2 you can choose in an infinite possible way. And they represent different measurement.
Sure.
Question is, when you are assigning definite value to a projector, say phi 1, this is phi. If you give it 0, then in whichever measurement context it appears, you will always give it 0 or not.
In local variable.
In hidden variable theory. If you tell no, I will give one projector just one value, which can be 0 and 1. If that measurement context change, still I will not change the value. Then it is called non-contextual hidden variable theory. Because same projector may remain in different measurement basis. But you stick to this point that I will give a value to a projector which I will not change even if the measurement context change. Then it will be called non-contextual hidden variable theory. What Kochen-Specker and Bell proved that non-contextual hidden variable theory will not work. Huh?
Hidden variable theory was rejected.
No, that is a very wrong statement. Yeah, you cannot tell that.
Quantum mechanics of course.
Two class of hidden variable theory are rejected. One is non-contextual.
Sorry to interrupt. Please use the other mic. It's a request to the classroom audience. Please use the other mic for questions or comments because there are people online who are listening. Thank you.
Question, shall I repeat the question?
Okay, the question was about the hidden variables from going from 2D to 3D. So we came to a point that I made a statement, the hidden variable theory has been discarded. But the speaker is telling that in some cases it is true, but in some cases not.
No, let me be very clear. By Koch and Specker theorem, and Bell also proved this thing, a class of hidden variable theory is rejected, and that class is non-contextual hidden variable theory, which does not care the context but assign value. That theory is in contradiction with quantum mechanics. And Bell's theorem tells that local realistic theory is incompatible with quantum mechanics. That means two class. One is non-contextual hidden variable theory, other is local realistic hidden variable theory. These two classes of hidden variable theory have been rejected by quantum mechanics.
Which class is rejected?
Of course, non-local hidden variable theory, David Bohm's theory is just discussed. It is contextual as well as non-local.
Okay, thank you.
So any question from online audience? Hello, can you hear me?
I don't see any on the chat box, but there are participants if they want to ask.
You want to ask? So, can someone help in mic?
Thank you for a very nice talk. I have a simple question. So when you mentioned about the device independent randomness, that 20% that is the lower limit, right?
Yeah, you cannot go beyond that.
So I had a
But you would be very, we will be very glad if it is 50% even under no signaling theory. But for just Bell's violation by 2√2, you can go at most go to 2080.
So I had a question with respect to violation of Bell's inequality by which was proven by Zeilinger's experiment, the starlight experiment. So in that, since the source of light that was used was starlight, to rule out any possibility of correlation between the photons, even the device. So I wanted to ask that in that case, we can say that it could have reached the 20% limit because even the starlight was probably not correlated with each other, even the devices.
It depends on very much correlation. The entangled state you have to produce. In a very definite way, you have to produce an entangled state of 2 photons or 2 other qubits, and then perform the measurement, collect the result, repeat it again and again, collect the statistics, then calculate and see whether Bell inequality is violated. This correlation is not, it is not only correlation is important, it has to be quantum correlation. That means entangled state.
Hello, sir. Good evening. My question was does wave function collapse violate time reversal symmetry?
Yes?
Is my question clear?
No.
So my question is कि does wave function collapse violates time reversal symmetry?
Violate time reversal symmetry, time reversal.
Yeah, collapse is not time reversal, where Schrodinger equation is. Yeah.
Thank you.
Any other question from the audience?
Hello, Arpita, কেমন আছো?
So, Guruda, Bell inequality that we are getting the successfulity from Bell this describe that. So that is 85% and 85. So success probability is 85%. In classical domain, it's 75.
Yeah. Even locally realistic domain, it is 75.
Yes, yes. So, but you are saying that 80-20. So,
Oh, 80-20, I am telling that. So there are 4 observables. Okay. 4 observable. Say, you are getting Bell violation. Then if you believe in quantum mechanics, then probability of getting up and down for all these 4 observable is 50%. Now you want to find that you get that under no signaling theory, if you get violation 2√2, then you are looking at what is the highest deterministic case of these 4 observable. So if you get 50-50, it is completely random. Then 40-60 is better. Better means you are trying to go lower side. So, but you cannot go below 2080. That means 1090. Sorry, yeah. You cannot. 2080 means, but it cannot be worse than this in terms of randomness.
no, so what is my so suppose I am running that Bell game several times for n many times. Now and I am doing this in ideal condition. So the probability of success is 85% and probability of failing is
No, in actual measurement you will get 50-50 in quantum mechanics. But under no signaling,
yes, yes. I am assuming that no signaling.
Then you can at most claim that 2080 it is.
Okay. And from that, then we extract that one.
Oh, that means it cannot be 1090.
1090, yes.
1090 is closer to determinism.
Yes, yes. So then after that, we can apply that von Neumann randomness extraction that you said that.
Yeah, if there is randomness, seed randomness, then you can amplify it.
So, in the theory, say some theory or and then you find this 20-80, this kind of randomness. So do you think that can be used to do something, some communication task?
I mean, if you know randomness, like there is a lottery game, then at least you can assure people who does not believe in quantum mechanics but believe in no signaling condition, then you can convince them that, okay, if it is not 50-50, it is at least 20-80. But in actual experiment, doing with quantum mechanics, and there will be actually it is 50-50. But the strength is coming from here that at least even if quantum mechanics is not true, still there is some randomness. That
No, what I want to know is, suppose in future somebody develops a new theory,
Yeah.
not quantum theory, and finds that this kind of randomness is still there. So do you think that can be used to do some secret communication or something, or?
For randomness generation, it's okay, but I have not talked about the other part. It gives device independent cryptography also. Device independent. I mean, Alice and Bob will have secure key. No third party will get any information.
But then that won't be as secure as device independent quantum.
When you are going to device independent, the rate will be lower. For quantum mechanics, it will be higher. But you are not caring about quantum mechanics. You are telling a statistics and no signaling theory. Then in every case, rate is lower.
So any more question from audience? No. Okay, so let's think once more on the block.
Thank you.